Hello everyone, my name is Ashfaque Alam. Welcome everyone here to this training session today. I'm the consultant physicist here at the Solar Energy Research Lab of Sheffield Hallam University, and today I'm basically going to talk about the IV measurement system that we have. This is the IV measurement system with which we measured the efficiency of the solar cells and some really necessary parameters as well. So in the first part we'll be talking a little bit about how the illuminated IV measurement is done and how it's helpful for our research. So when I talk about illuminated IV measurement, what we mean is basically we have an illumination which is simulating the power of the sunlight, and with that we basically try to find out that based on the input power in the form of light given to the solar cell, how much of the output power that we are getting as a form of electricity. So while doing that, we follow, I will not go into the detailed device physics. What I'll do is I'll basically show the simple formula that we follow to find out the power. So if I take a look at this formula over here, this is the formula for efficiency. So we give in an input power. The input power is given in form of light using a lamp, and we find out the value of VOC, JSC and FF, which is fill factor, which is open circuit voltage, short circuit current density and fill factor. So these are the three parameters we find out from the illuminated IV measurement. So the illuminated IV measurement is the measurement by which we find out these three parameters, and these three parameters give us the value of output power that we get after the input power is given to the solar cell. So in our lab, the solar cells are made with a substrate technique. So there are mainly two different techniques of fabricating solar cells. One is superstrate technique and the other is substrate technique. So to keep it simply, I would say the substrate technique is the technique of fabricating solar cell, where the first layer is the window layer. That means the first layer is the layer through which the sunlight will come at the first instance. So the solar cells that we make here in our lab are looking kind of like this. If I show you, there is a glass substrate at the beginning. On the glass substrate there is an FTO layer. So FTO is fluorine doped tin oxide, which is a conductive, transparent conductive oxide, which means the oxide is transparent and it is conductive. On top of that FTO layer, we basically fabricate our solar cells. That means we deposit our semiconductor layers. It can be N-type semiconductor. On top of that, there can be N+ semiconductor or P-type semiconductor. And after that semiconductor, last semiconductor layer is deposited, we deposit the metal contact, which can be gold, which can be silver, which can be aluminium, which can be indium, anything. So for example, in this animation we have shown the gold contact. So we can see that there are mainly two conductive contacts. One is the one at the beginning. This is the TCO or transparent conductive oxide, and there is another conductor which is the back contact, which is the metal contact, can be of gold, aluminium, silver or indium, depending on what the device is requiring. So we have this one contact over here, we call this a front contact, and there is this another contact which is called the back contact. Now if I show you one of our real devices, that will be even more helpful for you to understand the device structure that we're using here. So this, you can see over here, is a transparent glass, but this is basically a glass which has been deposited with an FTO layer, which is a transparent conductive oxide layer. So this looks transparent, but there is a thin layer of FTO deposited on top of it, and this layer is conductive. So on top of this we have our N-type semiconductor. For this is the cadmium sulfide semiconductor we have. So this yellowish or greenish yellow layer that you can see is our N-type semiconductor deposited on top of the FTO. And on top of that we have our P-type or N+ type semiconductor, and on top of that we have our gold contact. So like this is the finished device that we have just seen in the animation, and if I show you, this is the front contact, the transparent one, and the gold one is the back contact. So the contacts are necessary to understand the instrument that I am going to train you about. So at the first instance, what I am going to tell you is how the contacts are actually used for the measurement. So for IV measurement we basically have current and voltage. So we supply a range of voltage and we basically have a current resultant because of that supplied voltage. So what's happening here is we connect one probe to the front FTO layer and we connect another probe to the back gold layer. So this is the schematic. We will now see how it is done on the real instrument. So this instrument over here we have, this is called a ReRa tracing instrument. It comes with mainly two different sections. One is the IV measurement section, and there is another called the lamp power supply. The lamp works as the simulator of the sunlight. So at the first we basically turn on all the machineries that we have. So we turn on the power supply for the lamp, we turn on the power supply for the IV measurement system. Then we turn on individually all of the measurements. We wait a little bit because the lamp needs to, especially the lamp needs to warm up a little bit to be turned on. And then the first thing what we do is we open the shutter. If you can take a look here, this is the shutter opening system. We open the shutter, and if I take a look here, the lamp is now turned on. Okay, so like I have shown in the first equation, the first formula, that we basically need to give in some input power at the beginning, and we need to know what that input power is. So if I once again come here and show you, the power input normally for this standard measurement we give is 1000 watt per meter square. So in here we have a system of measuring what is the power of the light that is coming in. Okay, so for that what we first need to do is we need to open the software that is coming with the system. So the software, it's called ReRa tracing software. On the screen, this is where it is located. If you just click on it, on this icon, the software opens itself. So the first thing that we need to do is we need to calibrate the device. We need to understand, and we need to always keep in mind that for every measurement we need to do the calibration of the instrument. And in order to do the calibration of the instrument, we basically first need to fix the input power and then calibrate the device with a given reference cell that comes with the instrument. Okay, so the first thing is setting up the illumination. So in order to set up the illumination, we go to measurement. So once we click on measurement, there is this section called set irradiance. Now I click on set irradiance. Yeah, sometime it can come up with different dialog box, don't worry too much about that. So once you click on set irradiance, this is the window you get. But make sure for the irradiance setup, you need a reference cell. So where is the reference cell? Let me show you. So this is the reference cell that comes with the instrument, and this is a standard silicon cell, solar cell. And if I show you how it's connected to the system, is that this silicon solar cell is connected to the back end of the IV measurement system. Okay, so this is the back end or the rear end of the IV measurement system, which is connected to the reference cell. Now this reference cell is used for the calibration of the instrument, and what we do is we simply put this face down on the sunlight or the lamp in this case. So we can basically position the frame a little bit in order to make the light coming properly, and then we simply cover it. So if you remember that the reference cell is connected to the rear end of the IV measurement system. So before we measure it, we basically need to fix it on the system over here. So how do we do it? So before we start the irradiance measurement, we go to the hardware setting. Okay, we come to the irradiance measurement part over here. So in the irradiance measurement part, we have reference cell. If we click on it, it is already selected rear because there are two options, front and rear. We already know that the reference cell is connected to the rear end of the system, so we click rear. Okay, so that is all set now. Now we once again go to the set irradiance part and we click on measure. So we can hear that sound, beeping sound, and if I take a look at the irradiance over here, we will see it is 598 watt per meter square. But as you can remember, we need it to be 1000 watt per meter square, and for that what we do is we use this knob over here. So this knob, we can turn it clockwise to increase the power, and then click here to measure it again, and it has increased to 612 watt per meter square. So we need to increase it more. So we increase it more and then measure it again. We increase it more, measure it again, more, measure it again. So sometimes what happens is, if this is misplaced, then the irradiance measurement can be coming wrong. So we need to make sure it is placed properly. Once again, let's try it here. So we click on here, measure. Now you can see the irradiance is more than 1000. So we basically need to turn it down a little bit and then check again, check again, check again, it's almost there. We need to fix it to, if you remember, 1000 watt per meter square. Yeah, so like you see here, it has now, the input irradiance is now set to 1000 watt per meter square. So that job is done. We click OK. So our irradiance is now set. So the next thing what we need to do is we need to do the calibration using the reference cell now. So for that, the reference cell is already in the system under the illumination. So we click once again on the hardware setting. So we are now going to trace the curve. Okay, so for that we click on curve tracer, go to general, and once again you see it's selected front, but our reference cell is connected to the back end, so we click ReRa. Okay, so that's there. Now we start measuring the cell. So for that we need to select what type of cell it is. Like I have already told you, the cell is a standard silicon cell. We select silicon from here, and this is the illuminated curve that we are measuring. Okay, now before we click start, the last thing that we need to do is we just click on auto sweep range over here in order to set a voltage range that is going to be applied automatically by the instrument itself. So once I click it, that necessary setup is done automatically by the system. So then we go to start. Now when we come to start, once again we can see many options given here. The main things that we need to keep in mind is that our cell is a standard silicon cell. So we are doing the calibration. So I'm coding it as cal01. It's the standard sample, so we can say std samp, and cell number we don't need to worry about that. There comes aperture area. So when it comes to aperture area, let me show you something over here. This cell is a standard silicon cell, and you can see the cell inside this encapsulation is 2 centimeter by 2 centimeter, which makes it 4 centimeter square for the aperture area. So we are putting it here once again. So we now know what the aperture area is, and we set the aperture area over here. So we just write 4. The default setting is in centimeter square, so we don't need to worry about that. So it's 4 centimeter square. We have already set it up. Then the next thing we do is we click start. Once we click start, we will immediately notice that the measurement is running. So that means a voltage is being applied, and because of the applied voltage, the current is being traced. So this is the current versus voltage curve that we were looking for. Now, like I have already told, that from this curve there are mainly 3 different parameters we try to find out. One is the VOC, or the open circuit voltage. So the open circuit voltage is at the x-axis over here. So this is our open circuit voltage here. There is the short circuit current, or ISC, and this is our short circuit current. Now we need to find out the JSC, or the short circuit current density. For that we need to basically divide this value by the aperture area. And there is another parameter called fill factor, or FF, which is basically the ratio between this rectangle and this rectangle. Now all these measurements you can manually do it, of course, but the machine does it for you. So you can see for this calibration cell, for this reference cell, our JSC our VOC, our fill factor, they are all calculated automatically by the system, and therefore we can see that the reference cell is of 12% efficiency. So we now know that our device or our instrument, IV instrument, measurement instrument, is now set to go. So that ends the calibration part. So the next part is about how do we now use this system to measure our real life devices. Now I have already shown you one of our real life devices. Our devices are, once again I have told you, that are fabricated based on substrate technique. So we have some devices over here. I'm sorry, I'm looking for my gloves. Okay, there it is. So we have some devices available here. So this is one device that I'm going to measure the efficiency of. Now if you take a look here, each of these little dots are one devices. Why? Because this is the back contact of the device and this is the front contact of the device. So the light goes through this and we measure by connecting this transparent portion as the front contact and this golden portion as the back contact. So each of these dots, little dots, are one devices. So we place this device over here, the first thing. Now you need to remember one thing, that this contact, which is a micro positioning contact, is connected to the front end of the IV measurement system, and this is another contact or another probe that is connected to the back contact of the cell, is also connected to the front end of the IV measurement system. So this one is for the front contact or for the FTO, transparent FTO layer. This one is for the back contact or the golden contact of the cell over here. So the first thing first, I connect the, if I come a little closer, you see there are two very tiny delicate pins over here. So we basically need to connect these two pins to the transparent section of the cell, and for that we use the micro positioning here, and we basically turn it anti-clockwise to push it down on the surface. We basically need to be very delicate about it, make sure that we do not push it too tightly. The pins may break and that will be a trouble for the whole system, so we don't want that. So we gently but firmly make it sit on the transparent layer. So our front contact is made. Now comes the back contact. So for the back contact, we basically once again have another micro positioning system. Now the back contact is just one pin. There are no multiple pins over here. So we basically make it sit on our device, which is any of the golden dots that you can see here. So once again I turn it anti-clockwise to make it sit on the contact. Once again, we don't want to make it too tight, but that should be enough. So once it's done, I'm putting the cover off, and then I come back to the system again over here. Now the changes that we now need to make is, if you remember that for the reference cell, the connection was made to the rear end of the IV measurement system. Now for the real device, our
curve tracing needs to be from the front end of the IV measurement system. So we change it from hardware settings, go to curve tracer, go to general, and then we click on front. So that's it there. Now before we start our actual measurement, once again we need to change this to this particular device is a cadmium telluride device, so we select it as cadmium telluride. Once again it's an illuminated curve, and once again, if you remember from previous, we basically click auto sweep range so that the range of applied voltage is selected by the instrument automatically. Then we click on start. Now once again it comes up with many different parameters over here, but remember these parameters are supposed to be different from the reference cell we have, because this is a real cell we are measuring. So our device, if you remember, I have already told you that each of the dots are one devices. So previously we have seen the reference device, which is a rectangular device, but these devices are in circular pattern. So for circular device, in order to find out the area, aperture area, we basically need to know the diameter of the cell. And for this particular cell that I have put in the system, the diameter is 2 millimeter. So I select 2 millimeter over here. So once I select 2 millimeter diameter here, the system is programmed in a way it has already taken the aperture area into account. So the aperture area has already been calculated. So the next thing that we do is we can basically set a code for our device. We can say it's the sample number 1. Okay. Nothing else needs to be changed. All we need to do is basically we click on start and wait for the system to measure the IV curve. Once the measurement is over, the IV curve is supposed to be generated over here. So now that the IV curve is generated over here, you can see that the IV curve is not as good as the previous device. It's more like a straight line, but still you can basically get some VOC, some value of ISC, some fill factor, and you can get some value of efficiency as well. So what we can see is basically the device that we have measured over here. It's probably not as good, but it is a working solar cell. So now when it comes to efficiency in our lab for real devices, we can basically have ranges of different efficiencies starting from 0 point something to up to 15-16% efficiency. So it depends on how the devices are fabricated, how good the techniques are, how pure the materials are, and so on and so forth. Many different parameters are involved. So the main goal of this session today was basically to find out how the IV measurement system can help us measure the efficiency of a real life device, and I hope we have done it. So after that is done, after we have measured our after I have measured our illuminated curve and find out the efficiency, we basically need to shut the system down. In order to shut the system down, first thing we need to do is we need to close the shutter, and then we power off the shutter. Then comes turning off the lamp, then comes turning off the power supply for the lamp, then comes turning off the IV measurement system, and then we can basically turn off the main switches. So that's all for the IV measurement system for illuminated IV curve, and the later section we will discuss about something else. Thank you very much.